Next-gen nuclear reactors are the most lucrative source of energy we can employ with today's technology. But being lucrative doesn't always translate to practicality, especially when economics is a variable. The extreme environments within the cores of fast reactors require specialized material engineering that has yet to be perfected to an industry standard. Efficient thorium-fueled reactors require a unique fuel system to maintain self-sufficiency. Today, we're going to learn about the thorium fuel cycle and the obstacles it and fast reactors face moving forward. Nuclear energy today emanates from the cores of thermal reactors. Thermal, in this sense, means that the neutrons causing fission are moving at the same speed as any other particle around them. These neutrons interact very strongly with atom nuclei and thus are very efficient at causing fission. This is why we see thermal neutrons in essentially all nuclear reactors. Since thermal neutrons are moving so slow and don't possess a lot of relative energy, the nuclei of atoms are sometimes able to simply incorporate this neutron within themselves, forming an isotope. This means larger and larger atoms and isotopes are formed and accumulate inside uranium-235 reactors, creating the signature toxic fuel waste. Thermal reactors seem burdened with this defect, but there's another lesser-known uranium isotope we can readily fission. That is uranium-233. Uranium-233 is actually a better fuel than uranium-235. While roughly 80% of U-235 atoms fission after absorption, that number is a little over 90% for U-233. But this isotope doesn't exist in nature, it must be created. This can be accomplished when a naturally occurring thorium-232 atom absorbs a thermal neutron. After absorption, it transmutes into thorium-233 with a half-life under 30 minutes, causing a beta decay into protactinium-233. This, however, takes a bit longer to decay, a half-life of almost a month. If it can last this month, it will then beta decay into fissile U-233. It is this half-life and the new chemistry involved that makes thorium a difficult new fuel source. The investment in the development of pipelines and efficient chemical processes to operate uranium-based reactors has to be undertaken again for thorium. The energy sector is not a lucrative investment opportunity, so funding from private entities to do so is not abundant. But research continues as some governments continue to fund it. Nuclear fuel needs to be enriched to an extent in order to sustain a healthy chain reaction. This blanket of thorium possesses no fissile potential, and it must sit for at least a month while bombarded with neutrons for any fissile material to form. This would be only a minor inconvenience, but unfortunately here we encounter thorium fuel's biggest flaw. Protactinium-233 has a neutron cross-section about 5 times greater than thorium-232. If Pa-233 absorbs yet another neutron becoming Pa-234, it will hastily decay into uranium-234, which is not fissile. Early on, this is not a big issue as the sheer amount of thorium absorbs far more neutrons than protactinium. But over time, thorium concentrations will decrease while protactinium concentrations increase. At some point in the future, the rate at which protactinium is created matches the rate at which it transmutes into uranium-234. This means we lose efficiency in that we cannot achieve faster burnup rates as our fuel concentration cannot be increased. It also means until the concentration of uranium-233 has increased, we need a little extra external uranium or plutonium to kickstart and maintain the core. This is still not a huge issue as fuel economy is greatly extended. The Oak Ridge thorium reactor extracted 75% of its energy from thorium. One of the selling points of thorium reactors is their breeding ratio, or the idea that for every atom that fissions, more than one atom of thorium will absorb a neutron and become uranium-233. This means more fuel is created than is consumed. One could then use that excess fuel to start another thorium reactor, eliminating the need for the outside fissile material. But as the concentrations of protactinium and thorium change, the breeding ratio decreases. There are some clever ways of arranging the field in the core which isolates the thorium further, or one can physically remove or rearrange cores to increase transmutation. The shipping port reactor experiment achieved a breeding ratio of 1.01. But this isn't as economically lucrative as one would hope. Fuel costs are not a significant concern with nuclear economics. Along with the more expensive manufacturing costs for solid fuel and heightened safety measures to handle it, there are legitimate reasons for the lack of thorium-focused research. In order to reap the benefits many of you have heard about, thorium fuel cycles require efficient isolation of the protactinium-233 from the neutrons in the reactor. There are no set-it-and-forget-it methods to do this. The heavily touted molten salt reactor is a design hoping to accomplish this. Thorium and uranium are dissolved into a liquid salt. This liquid enters the reactor where the uranium fissions, releasing neutrons which are absorbed by the thorium. The byproducts exit the core and are then reprocessed. This separates the components, allowing pure uranium and thorium back into the core and holding on to the protactinium-233. This process has not yet been perfected and is what holds back efficient thorium reactors. But, if conquered, due to the increase in efficiency from thermal neutrons and the abundance of thorium, there's no conceivable scenario where humanity would run out of energy before the next energy source becomes available. Since we are already so deep into uranium as a fuel source, the other option for next-generation reactors are so-called fast reactors, which use high-energy neutrons. Despite being less efficient, fast reactors can use more isotopes as fuel while producing less harmful waste in much smaller quantities. They also have a couple engineering hurdles to overcome to make widespread adoption feasible. The first question to ask is, why are fast neutrons less efficient? This comes down to the quantum nature of matter and that particles also move as waves. Higher energy wavelengths are shorter, whereas lower energy wavelengths are longer. Thus, when passing through a nucleus, it's more likely the slower moving, longer de Broglie wavelength of the lower energy neutron will interact than the faster moving, shorter de Broglie wavelength of a higher energy neutron. This means thermal neutrons have a higher likelihood of neutron absorption and subsequently a fission event. The ability of a neutron to cause fission after absorption is described by its capture-to-fission ratio. This is the ratio of atoms who incorporate the neutron into a heavier isotope versus those that undergo fission. When we look at this table, we can see that many transuranic elements disproportionately absorb thermal neutrons. This causes a buildup of these heavy elements in the waste. When absorbing a fast neutron, that excess energy more readily destabilizes the nucleus, making fission more likely. Thus, we see a stark decrease in the capture-to-fission ratio in large nuclei. This is what makes fast reactors so attractive: their ability to fission larger, long-lived isotopes that would make the waste dangerous for tens of thousands of years. Maintaining these high-energy, fast neutron environments is where fast reactors become less attractive. The heat generated in nuclear cores needs to be transferred to some sort of mobile phase. This mobile phase transfers the heat to another compartment to boil water, which ultimately spins a generator. Since thermal reactors need slow neutrons, they can use mobile phases that readily interact with and slow down neutrons. Water excels at this and as such is used in the majority of thermal reactors. Mobile phases for fast reactors are a bit trickier, the caveat being we don't want this mobile phase to interact with or slow down the neutrons. Collisions of such small particles are almost perfectly elastic. Thus, if one object, our neutron, is much lighter than the other, our moderator, then after the collision it will still be moving almost the same speed. So fast reactors must use a heavier mobile phase which avoids slowing down the neutrons. These are either liquid metals or molten salts, both of which are not the friendliest of materials. Dunray and the Beloyarsk fast reactors both use liquid sodium, which reacts violently with the oxygen in the air, and both stations have experienced fires or explosions of their coolant on multiple occasions. As a result, many nuclear proponents suggest using a molten fluoride salt. This does not react violently with the air, but its implementation is still not trivial. Fluorine is the most electronegative element, and as such, fluoride salts are incredibly efficient oxidizers. This means they are very good at ripping electrons away from the materials around them, which over time corrodes and destabilizes pipes and containers. Hence why sodium is an attractive method. One potential compromise would be dissolving the fuel into the salt a la uranium chloride salts. Uranium chloride is mostly docile with low corrosivity, but uranium tetrachloride is strongly corrosive. Thus, you need a binder to react with uranium tetrachloride when it forms to prevent excess corrosion. Uranium chloride fuels require pretty high temperatures to remain liquid, but they allow high uranium solubility, so you can achieve some pretty efficient burnup rates once things are heated up. But this still isn't a panacea. Chlorine-35 can absorb a neutron, becoming chlorine-36. This isotope is radioactive. Using chlorine creates more radioactive waste, counteracting one of the biggest appeals for fast reactors. Thus, much like thorium reactors, the biggest obstacles for fast reactors is engineering reliable and economic manufacturing methods of producing these mobile phases and new materials for containing the more corrosive ones. Energy is the backbone of everything. Life and well-being will only improve with more energy. Greener and sustainable technologies become more feasible with cheaper energy, and cheaper energy will lead to more rapid economic growth and expansion. The societal returns on investment in new energy sources are the most lucrative a society can achieve, as they will impact every sector within it. The only issue is that the monetary returns of the energy itself aren't worth the investment for those trying to profit off it. So unless governments or every sector that uses energy wants to make an investment, it'll be a little longer until we see this technology become widespread.